Okay, so I want to do number 19 in 18.2, which says I need to calculate the line integral of f, which is 2x minus y plus 4, comma 5y plus 3x minus 6, over the triangle with vertices 0, 0, 3, 0, 3, 2, traversed counterclockwise. Which way is counterclockwise? The opposite of, for me or for you?
For you,
For the board, whichever way you look at it.
counterclockwise.
Look at the
Yeah,
board.
so look at the board, right? And envision a clock. Clocks go that way, so counterclockwise is this way. Which, it should be noted, is, so think about counterclockwise as mathematically positive. Why do I think counterclockwise is positive mathematically?
Sine, cosine, the
Yeah, my usual sine cosine parameterization of the unit circle goes counterclockwise, right? So there's another good reason for this, which we'll get to today actually, but Green's theorem also goes by default counterclockwise. Cool?
And that's what the quadrants are too, right? Don't they go 1, 2, 3, 4?
Yeah, that kind of, there's lots of reasons for this. Green's theorem is kind of the primary. That was a choice though. There was no like God-given mathematical reason that had to be the case. Okay, so how do I do this? What do I need?
Start with the segment from 0, 0 to 3, 0.
Yeah. Fundamentally, right, if you're going to do a line integral, you need to parameterize some curves. I have, however, 3 bits to do, right?
So you probably just add them together.
Yeah, so I'm going to split this into 3 separate line integrals and just add the results, right? Okay, so on this guy, my first like R, I don't know, I'm going to call this bottom, right? What's R bottom of t? What's your parameterization to do the bottom curve here?
0, 0, 3, 0? Is that what you're looking for?
3T, right?
Yeah, I want to go from 0, 0 to 3, 0.
3T from 0 to 1.
Okay, so you want to do the vector function 3t comma 0, and that forces t's to live between 0 and 1. What if I did 0, or what if I did the vector function t comma 0?
Then the t's would look like that.
Then we'd go 1 to 3 instead of,
0 to 4.
or sorry, 0 to 3 instead of 0 to 1. But whatever, it would come up in the wash. Cool? All right, I think I also need R, I don't know, I'm going to call that one right, because it's the right side of the triangle. So that one's going to be, what's your parameterization there?
0 to 2t.
Well, I think it's actually, this is the thing that I got wrong. It's 3 to t, isn't it?
It is, in fact, 3 comma t maybe, or 3 comma 2t. Why? Well, what's the x value in there?
3.
Yeah, the x value is always 3, right? And the y value is ranging from 0 to 2. So my t's, right, are from 0 to 2.
Do you think it'd be easier if you made that 2T and make it just 0 to 1, or would it be the same?
It makes no difference.
It won't make any difference at all. Probably it would be a good idea to keep things consistent, but I've apparently settled on this. Okay, and the hard one, our hypotenuse of t, which is,
It's like, first you start at the position 3, 2, which is the big problem here.
you guys see this? So I'm thinking about this as a line, right? So there should be a starting position, that's that 3, 2 thing, right? And to that I should add some kind of slope times a time, right? So what's your slope in there?
Negative.
So what's that vector?
Negative 2/3.
Positive. Well,
That's negative 3 comma negative 2, right? You guys all with me on this? So ultimately here, I get RH of t is what?
3 minus
3
3t.
minus,
I do 3t and then the 2 minus 2t as the other one.
perfect. So 3 minus 3t. Right, so as t goes from 0 to 1, that's going to go from 3 to 0. Okay, good. I'm getting the, whoops. I'm getting the x thing happening out of this. And then the y thing that I need to happen is it needs to go from 2 down to 0, right? So I need 2 minus 2t. And then how am I sure this is the curve that I'm looking at here?
Plug in 3, 2, and
Look.
0.
Look at the two positions.
Okay, careful. Just because it starts in the right spot. So if I plug in t as 0, it starts at 3, 2. If I plug in t as 1, I get 0, 0. So it starts in the right spot, ends in the right spot. How do I know it's the line that I'm talking about?
Those are
Because
linear
of
functions.
Yeah, good, because this is a linear function. You guys see that?
Right.
There are other curves that could do that, right?
Mhm.
Like this one or
Yeah.
something.
And we can't prove that it's conservative, so that's bad if we don't know that.
You guys all good with this? Okay, so I have 3 curves, and I need to integrate over each one.
I just wanted to ask a question. So RH, that's from 0 to t to 1, sort of?
Perfect, good. I forgot to write down my
Yeah.
t's.
I was
So
just,
that's 0t is smaller than 1.
if it was originally just like 3t, 2t, could we have done from 1 to 0 instead? Or, I understand it's not exactly written the same way, but.
Oh yeah, so
Reverse
if,
the integral.
if I use the other slope,
Yeah. And then basically.
yeah, you could run time backwards to make this happen. So
Okay.
yeah, there's some fiddling with time you can do here.
Mhm.
You guys all see that? You just want to make sure that it starts at, when you plug 0 in, you should be at the point you should start at. When you plug your upper bound in, you should end at the point you ought to end at, and the category of function should match.
Okay.
Guys cool with that? Okay, so I think my integral over c of f dotted with dr, right, has become what?
Okay, so it's 3 different integrals.
Okay, so there should be 3 different integrals.
So the first one is dotted with the RB. So
Okay, so the first one should be over rb. So where do your bounds go on rb?
0 to 1.
0 to 1. Okay, so this guy I'm thinking is the rb integral. This next one's going to be the r.
R. Yeah.
That was a good naming choice, Joe. What a dummy I am.
That's 0 to 2.
So that's the lower r sub a bigger r integral. And that one should go from 0 to 2. And then this last guy,
R sub h, which is 0 to 1.
that should be the r sub h integral. And that should go from 0 to 1. Everybody good with this?
Yeah.
Okay, now I need to evaluate f at each of those separate pieces, right? And then I should dot with what and put a dt. Good, yeah, that should be the derivative, right? So, yeah, of each different r. So the first rb derivative, right, is what?
3, 3.
Okay, the vector 3 comma 0. Okay, and the one for r ought to be
0, 1.
0 comma 1. And the one for RH ought to be -3, -2. Okay, cool. Everybody good with those? Okay, now what's f evaluated at RB?
So yeah, RB is 3t0
So I'm taking this, RB, right, and I'm plugging it in
to the f function itself.
to your vector field f, right? So you got, on this one the y's are 0, right? So I can ignore the y's.
6t plus 4.
Good, so I got 6t plus 4, comma,
9t minus 6.
9t minus 6. Cool. Right? Okay, next I need to plug r into that thing. So in that one I'm plugging in 3 and t, right? So you get 6 minus t plus 4 is, I think, 10 minus t. Okay, what if I made a typo there? Does it matter?
No. Oh, wait. Yeah.
Like, what if I made an arithmetic mistake?
It's fine because it's gonna get dotted with a 0.
Yeah, I'm dotting with 0 anyway for that piece, right? So who cares if I screwed that one up? Right? I literally didn't need to do that. I just wasted my time. Shit. Okay, on the other one though, this one matters because I'm going to dot with 1, right? So that guy ought to be what?
5t plus 9
5t plus 9 minus 6
so it's gonna be
is
5t minus 3.
5t minus 3, I think?
Plus 3, sorry.
Plus 3. Cool, cool. Okay, and last one is going to be annoying,
Yeah. I'm sorry.
right? Because that one's going to be a big mess.
And
Okay.
both matter.
So, and they both matter. So let me carefully do that one over here. So I need 2 times, what's your x coordinate on RH?
3 minus 3t.
3 minus 3t. Minus, what's your y coordinate?
2 minus 2t.
2 minus 2t.
plus 4.
And then there's a plus 4. Okay, so that's 6 minus 6t minus 2 plus 2t plus 4.
That's negative 4t
So all told, I got negative 4t
plus 8, I believe?
Yes.
plus 8. Cool. Negative 4t plus 8.
And now the other half.
And now the other ones. So the other one, I need 5 times, what was y?
2 minus 2t.
2 minus 2t plus 3 times 3 minus 3t
Yep. Minus 6.
minus 6. Okay, so I got 10 minus 10t plus 9 minus 9t minus 6.
So negative
Negative
19t
So negative 19t
minus
plus
25.
13, I think.
Oh, right, because those are pluses. Yeah.
So 19 minus 6 is 13. Great. So I got minus 19t plus 13. Whoa. Now what?
Now we just kind of figure it out.
Yeah,
It's
okay.
like
Now
we
you
have
need
all
to
the
dot
time.
everything, right? So you got, this guy is the integral from 0 to 1.
18t minus 12, I believe.
I think I got 18t plus 12.
Oh, is it a plus? Oh, that's plus 4. Okay, sorry. My fault.
I don't know why you're apologizing. It's just as easy that I made an arithmetic or transcription error. Plus the integral from 0 to 2 of what? 5t plus 3 dt. Plus the integral from 0 to 1 of, oh crap.
Let's see.
So I got 12t minus 24
And
38t.
yeah, 3t
plus
minus.
38t minus 26
Yep.
dt. Okay, and good news, that's
It simplifies to
40t minus 50?
50t minus
40, what?
50t.
Oh, that's 50. Huh.
Yeah.
50t minus 50.
Wait. It has a. Oh, I see what. Okay.
Okay, cool.
Yeah.
All right, so when you integrate these bits, what do you get?
So let's see, we get
9t squared
Yeah, 9
plus
squared.
You got 9t squared plus 12t evaluated from 0 to 1 plus 5 halves t squared plus 3t evaluated from 0 to 2
Yep.
Probably I ought to put parentheses around my evaluates, right? Plus 25t squared minus 50t evaluated from 0 to 1.
Yeah.
So yeah, parentheses there as well. Woof. So I got 9 plus 12 minus 0
21.
plus 10 plus 6 minus 0 plus 25 minus 50 minus 0 is some number. What do you get?
12.
Okay, that's minus 25. So that's minus 15.
96.
So that's minus 3. So that's 3. 12.
Yep.
I have no idea if you guys followed that, and I don't care. Add those numbers up somehow. Whatever's convenient, really.
Calculator. It's 12.
Sure. 12.
Yeah, that's
Yeah, I got that a long time ago. Come on, Chris. Keep up,
I
buddy.
did it in my head, bro.
I did it in my head. Yeah, and I did it on the board. Do you want a participation trophy?
No.
Okay, so I got 12. What the hell does 12 mean?
Yeah, you're fine.
Like the area of the curtain, right? That's how we think about these things.
That would be the work done from
Which-
one point to another, right?
Yeah, this is not a scalar line integral, right? This is a vector field line integral. So this is the amount of work that it takes. Well, not the amount of work that it takes. The amount of work that the vector field does to push something along this path, right? So I got 12, which means what?
You build up constant energy as you
Yeah, that you can go around this path and this thing will help you, right?
Just not necessarily.
Which means that this is not like gravity, right?
Nah.
This thing's not path independent. You guys see that? If it was path independent, if I went around in a loop, that would be the same as just sitting there. Right? So I would get 0 out of this. But this thing means that the vector field
Yep.
kind of helped you go along that closed loop, right?
It's like a lazy river.
Like a particle accelerator.
Yeah, this is a little bit like the vector field in a particle accelerator, right? You can go around a closed loop and add energy.
Except particle accelerators are not triangular.
Yeah, except particle accelerators are not traditionally triangular.
Yeah.
Because there's a small problem about you need to get these particles to make a right angle turn, which is problematic with that whole magnetic containment business that they do.
If you have like a path-dependent function for a circle, and say you have like with 10 like you have, if you would have run it twice, would it help you 20 then?
Yeah, so I got 12, right? So if I do this loop twice, the vector field will have done 24 units worth of work for me.
So that's how a particle accelerator works and adds a little more each time until it's going up and down.
Yeah. Yeah, a particle accelerator is just a big vector field that we've created that adds energy to the particles in it. Right, so one loop, you get a unit, one loop, you get another unit, one loop, you get another unit. You just keep doing that until you approach relativistic speeds and physics starts to kick in. Like the energy's still in there, right?
One thing we talked about on Monday with path independence and conservative. If you're conservative, doesn't that mean if you loop around to the same spot, you get 0?
Yeah.
This is not conservative.
So what I found is that this vector field is not path independent because I went around a closed loop and I didn't get 0, which means that this thing is not the gradient of something. Should we try to see that quick? Like, that's another thought, right? I know this thing about gradients, so I could be like, hey, maybe that sucker's the gradient of something, and then I wouldn't have to do all this freaking work. Yeah. So the first thing you really should try, actually, and this is seriously a good idea, is when you're approached with one of these things, you should be like, first things first, I'm going to spend 30 seconds and see if I can get out of this. Right? So the first thing I'm going to do is think to myself, hey, maybe that dude is the gradient of some little function f, right? So what would I know about that little function f if this was the gradient? Yeah, I'd get some path independence. I'd know the integral around a closed loop is 0.
Mhm.
Sweet. I don't even have to apply the fundamental theorem of line integrals, right? Okay, that would be cool. That would make this faster. So if this is the gradient of some function f, what do I know about that function? Like,
The derivative of its components is supposed to be that if it's its gradient?
yeah, if this is the gradient, then fx should be 2x minus y plus 4,
And
Right.
FY,
and fy should be
5Y.
5y plus 3x minus 6.
Yeah.
I've made an assumption here, right? So let me see how this works out. If you x differentiated and got this stuff, what is a function that has that property?
X squared minus YX plus 4x. Oh, plus C.
Yeah, so be careful with your plus c's, right? Because this thought is like an integrate dx, right? Like that's what you're doing.
Okay.
So the things that are constant here are constant with respect to
X.
just x, right?
Okay.
So these could be some whole function of y's, right? Because that plus c should be constant with respect to x. So it might be constant as a, like, with respect to x, which means it could be a giant function of y,
Okay.
right? Like that could be sine of the log of 4y plus 17 plus 30, right? Like that would be totally fine. All that crap's constant with respect to x, so when you differentiate, it goes away. You guys cool with that? Okay, what about this guy? That's the y derivative, right?
Yep.
So if you integrate,
5 over 2y squared plus 3xy.
okay, so you're kind of integrating dy,
Oh,
right?
yeah, sorry.
No worries. So you got
5 over
5
2
halves y squared
plus
plus 3xy
minus 6y
minus 6y plus,
gx.
yeah, maybe some constant that depends on x. I don't really care what symbol you use for that. I probably shouldn't have used this. You guys all good with this? Now, I would like for these two guys to give you the same answer, right? Those should both be f. You guys all with me on that?
You're referring not to the constants, but to the whole thing.
Yeah, like this thing should be f, and so should this thing.
So in other words, g of y should be like 5 over 2y squared minus 6y, so that's...
Yeah, so let me see if I can just basically balance these equations, right? You guys kind of with me on that?
Yeah.
So I'm just going to go like this. I'm going to go, okay, so x squared minus yx plus 4x plus g of y should be 5 halves y squared plus 3xy minus 6y plus some constant of x, right? Okay, so which things can you account for?
The 5 half y squared and the 6y on that side?
Okay, like this dude here can be a part of g.
Yeah.
And 6y?
Oh, so can the 6y. The x squared and the 4x, those guys can be accounted for in the c of x, right? So what's the, what am I left with?
Negative
Negative yx and
equals,
minus 3xy.
Shit.
Yeah.
It's not
You guys see this? Like this just isn't gonna happen. So this thing's not the gradient of something. The vector field I started with isn't conservative, so this fell apart on me. I guess I have to do the other thing. You all see that thought? So you should try this for just a second. Don't fall into this trap, right? Like this thing can take a while. If it's not immediately coming to you what that function f is, don't sweat this thing. Like just quit. Line integrate. It's not that hard to parameterize 3 curves. You can just do it. You guys see that? If you get 0 at the end, great. Right? If you don't get 0 at the end, well, then this wasn't going to work anyway, and trying it for a long time was wasting your time. You guys cool with that?